Imagine a missile that can punch through meters of reinforced concrete, burrow deep underground, and then explode inside. How does that even work? What raw materials, technology, and engineering go into making a weapon that can bunker bust? In the next 5 minutes, you'll discover the hidden world of bunker buster missiles, from dense steel alloys to precision GPS guidance, advanced explosives, and the testing that makes them field ready. Stay tuned, because by the end you'll understand the secret behind these penetrating beasts, and what it takes to build one. Underground bunkers are designed to survive bombs and rockets. They're built with multiple layers of reinforced concrete, often more than 10 feet thick, buried under earth and rock. Simply hitting the surface isn't enough. The surface may crack, but the real target, command centers, missile silos, stockpiles, remains protected. So how do militaries get past that? Enter Bunker Busters missiles, purpose-built to penetrate hard targets, dig deep, and detonate precisely at depth. But that isn't easy. Pressure spikes on impact can shear off a conventional warhead. Aero force can break the missile apart, and faulty timing could cause secondary or surface explosions, failing the mission. Bunker busters are engineered specifically for strength and accuracy. Their casings are made from high-density heat-treated steel alloys, sometimes with tungsten reinforcements, to survive massive deceleration forces. Their nose cones are bombarded with ceramic or composite nose tips that disperse heat and cut through concrete. The shapes matter too. Many bunker busters are long and slender, like a thick arrow, to concentrate kinetic energy. They may also have copper or aluminum liners to help shape the blast once inside. And the high explosive fills are often thermobaric or insensitive high explosive, packed tightly, designed to get maximum blast impact at depth, not wastefully explode on the surface. Precision is key. The missile must hit exactly where it can penetrate deepest and detonate milliseconds later. That requires advanced guidance and fusing systems. Everything starts with raw materials. Steel alloys are chosen for hardness and malleability. These are forged into seamless tubes with precise tolerances, no defects, using CNC machines and hydraulic presses. Each casing is X-ray and ultrasonic tested to detect internal flaws. Any imperfection could cause the missile to snap on impact. Nose cones are crafted from tungsten carbide or ceramic composites. Engineers design them using CAD and test their aerodynamics using computational fluid dynamics, or CFD. Once finalized, nose cones are lathe-turned and fitted with sensors to record impact speed and stress during live tests. Inside the casing, the guidance package is assembled, inertial measurement units, GPS receivers, microprocessors, and sometimes laser sensors used during the terminal dive. The fuse, the brain that decides when to detonate, is engineered to resist massive shock. It's enclosed in Puna-rated shock mounts and programmed with multiple sensors to ensure correct timing. Once the casing is sealed and electronics installed, it's time to add the warhead. Technicians pour or press the explosive, like PBX or plastic bonded explosive, into the cavity. The fill is done under strict safety protocols, temperature-controlled rooms, remote handling equipment, and constant vibration testing to detect voids. Heat shielding is added if needed. Fins and EDF or electro-detonation fuses are installed. The missile is sealed, labeled, and sent to Factory Acceptance Testing, or FAT. That involves drop tests, vibration tables, temperature extremes, and inert flight tests. Only after passing those does it move to live fire qualification rounds. A bunker buster isn't ready until it's proven. In live fire tests, missiles are dropped from aircraft or launched from platforms into concrete and soil bunkers. High-speed cameras track penetration speed. Seismographs and sensors inside the target bunker record blast force and timing. Engineers analyze every millisecond. Did it go deep enough? Did it detonate at the right point? Did the electronics hold up? If not, they go back to the lab, adjust alloy composition, tweak guidance software, redesign shock mounts, and then test again. This cycle ensures reliability in real-world missions. From raw steel to explosive core, from CAD designs to live fire testing, bunker buster missiles are marvels of material science and precision engineering. They're a testament to human ingenuity, built to solve a seemingly impossible problem, busting through fortified underground hideouts. Now that you've seen the full process, what amazed you most, the reinforced nose, the electronics that survive impact, or the final test firing? Drop a comment below and tell us. If you love diving into military tech, hit like, subscribe, and ring the bell for more breakdowns of secret weapons and advanced engineering. Thanks for watching, and I'll see you in the next one.